My primary areas of research are in numerical methods and differential equations, but I decided that since this is my farewell lecture, I try to pick a topic that's a little more accessible. And so instead I'm going to describe my 25 years of activity in an area known as musical geometry. Let me begin with a little biographical information. I have musical genes. My grandfather, Doc Kelly, was a professional trombonist during the early days of the big band era, and his brothers played saxophone and trumpet. And when I was a wee tyke, Doc tried to teach me music basics by showing me chord progressions on his ukulele, but I must confess I wasn't a very good student because I was distracted. And the reason I was distracted is when I was in the first grade, something momentous happened. And that is, this was in 1957, the Soviet Union launched the Sputnik satellite. And this began the space race. And the United States began to allocate large amounts of money to education in the sciences and engineering. And I was swept up in this wave. I wanted to be a scientist worse than anything. The problem is I couldn't make up my mind what type of scientist I wanted to be. I wanted to be an entomologist. I wanted to be a metallurgist. I wanted to be a bacteriologist. I wanted to be a nuclear chemist. I wanted to be an astrophysicist. And the way I finally resolved all these conflicts was I discovered that if I went into mathematics, then I could do them all. And I could do them all. So that's precisely what I did. I went to the Quran Institute and got my PhD in mathematics and went to work for United Technologies as senior research mathematician. And there I worked in a wide variety of engineering and scientific disciplines. But in 1989, I had an opportunity to move on and become computer science chair at RPI Hartford. And this was a graduate program that was completely at night. Okay? All the students were working professionals, and that meant that for the first time in my career, I was free during the day. And I discovered that we had a reciprocal arrangement with neighboring educational institutions where faculty could take courses at no charge. And so I enrolled at the Hart School of Music, which is a conservatory attached to the University of Hartford, and I began to study music theory and piano. And in the music theory classes that I took, I was bowled over by how mathematical it was. The problem being they were using mathematics that was not my strong suit. Classical discrete mathematics, group theory, combinatorics, graph theory. I'm more of a geometrical thinker, I think in terms of diagrams. And so what I began to do as a student, and I've continued since then, is I essentially developed a geometrical approach to music. So I've gone back and I've produced my own proofs of all the basic theorems of music theory, but they're all pictorial proofs. And I want to describe one of them to you today. Okay. Now, when I came to Kettering in 1993, I had not yet finished my degree. I had my thesis to finish, and I did that on the weekends at University of Michigan Library. The title, if you're interested, was Haydn, Mozart, and the Classical String Quartet Fugal Finale. That's a mouthful. But by 1998, I had assembled enough geometrical proofs of musical theorems when I went public with this endeavor. And I published a paper called Prelude to Musical Geometry in the College Mathematics Journal. And this paper has gone on to be one of the most cited papers in music theory. If you go to any of the Wikipedia sites that talk about circle of fifths or modulation, all of them refer to this paper. Okay? And the figure that you see in the front, this was the cover story for this month, November of 1998. This was drawn by my present wife, Barbara, and therein lies a musical story. When I moved to Flint, I wanted to continue with my piano studies, and I did so by enrolling at the Flint Institute of Music, where I met Barbara. She was also a student there, and we began to play duets together. In fact, we have performed here at McKinnon Auditorium in the past, and we perform under the moniker of the Killer Bees, Barbara and Brian. I somehow cajoled her into illustrating the figures in my papers. So all of the figures you're going to see today were done by Barbara, and all my subsequent papers have been illustrated by her. Now, movie stars, when they make it big, they get a star on Hollywood and Vine. But in mathematics, we have something called Carriage House. It is the center of the Mathematical Association in Washington, D.C., and they have a brick walk called the River of Bricks, and Barbara has a brick there commemorating her mathematical artistry. So I want to publicly thank her. Now, in order for me to describe Cohn's theorem, which I'm going to focus my talk on, I need to first provide you with some background in musical geometry. And so let's start with the very basics. We have our piano keyboard with this alternating pattern of black and white keys. And we need to know what we mean by adjacent keys. So for instance, this B and this C, they are adjacent to one another. They're right next to one another. But the C and the D are not adjacent because they have this intervening black key. And in the way that modern pianos are tuned, so-called equal temperament, the musical distance between adjacent keys is the same. And it has many names. Sometimes it's called a semitone. Sometimes it's called a half step. And I'll use both names. So that's the musical distance between adjacent notes. Now, one consequence of equal temperament is enharmonic equivalence. And what that says is if, for example, if you take C and you raise it a half step, it makes it C sharp. If you take D, you lower it a half step, you get D flat. C sharp is equal to D flat on the piano. Now that might seem obvious to you the way the keyboard is laid out, but in effect is not true for Baroque tunings of harpsichords. C sharp and D flat are in fact different notes. And most importantly, we're going to make the assumption of octave equivalence. Anytime we try to apply mathematics to the world around us, we must make simplifying assumptions. The world we live in is simply too complicated to write down in terms of equations. So we have to simplify it first. And what octave equivalence is we're going to take, for example, these two C's, and we're going to consider them the same note. We're not going to distinguish between C's or B's or D's. And we do this all the time when, for example, we sing in a choir. Right? If the sopranos, the altos, the tenors, the basses, if they're all singing C, they're not singing the same C. Okay? But they sure sound like the same note. So we can get away with this approximation. Now, we talked about the musical distance between two adjacent notes, half step or a semitone, but it also has a third name. It's called a minor second. If there are two half steps between notes, it's called a major second. 3 is a major third, followed by minor third, followed by major third, perfect fourth, tritone. And so musicians use pi for 6 semitones as opposed to mathematics. Perfect fifth, minor 6, major 6th, minor 7th, major 7th in the octave. Okay? So those are the intervals that are possible between pitches on the piano. But because of our assumption of octave equivalence, we can winnow this down to 6. And we can see that as follows. We're going to have to identify two intervals if they are complementary. And what that means is if they add up to 12. So for example, perfect fourths and perfect fifths we're going to consider the same because 7 plus 5 is 12. And why is that? Well, if we go back to the keyboard for a moment, if we start at this C and we move up 7 half steps, we get a G. So that's a perfect fifth. Up is a G. If we move down 5 half steps, we land on this G. That's a perfect fourth. But we already said a moment ago those two G's are the same. So we have to consider those two distances the same. So there's no difference between a perfect fourth and a perfect fifth in this mathematical model. Now, by the assumption of octave equivalence, we've reduced our keyboard of 88 notes to simply 12 notes. And then we can take those 12 notes and assign them to the hours of a clock, right, where I've called 12 o'clock 0 o'clock. That's what we mathematicians do. So we can assign the 12 notes to those, and then we can perform what's called modulo 12 arithmetic on them. We do this all the time when we read the face of a clock. For example, if we start at 3 o'clock and we go 13 half steps clockwise, well, 12 will bring us all the way back to 3. One more will bring us to 4. 13 plus 3 is 16, divided by 12 leaves a remainder of 4. So 13 plus 3 in this arithmetic is 4, not 16. Okay? And we can even get more geometrical. If we play more than one note at a time on the piano, we call that a chord. And so what I've got shown here is a C major chord, a C, an E, and a G. But if we connect the dots here with straight line segments, we see we get a polygon, in this case a triangle. And so all of a sudden we find ourselves in the land of musical geometry. We can talk about these polygons associated with chords. And we can subject them to geometrical transformations. So for example, we can take the chord and we can rotate it either clockwise or counterclockwise. There are 12 ways to do that. In music, this is called transposing the chord. So transposition in music is the same as rotation in mathematics. And the group of the 12 rotations is called the cyclic group. It's a famous group in group theory. Okay? So we're heading out into deeper water now. Now, in addition to simply rotating the pitch polygon, we can reflect it in a mirror. For example, we can take an axis between 12 o'clock and 6 o'clock. So imagine that there's a mirror there and perform the mirror reflection of the chord. In music, we call this an inversion of the chord. And if we take these 12 inversions or reflections and combine them with the previous 12 reflections, we get what's called a dihedral group in mathematics. So we can begin to start to apply some of the theory of symmetry groups to the study of music. Now, here is the most important collection of notes in Western music, at least. Right? Almost all of Western music is built on these 7 notes, the so-called diatonic scale. So what we do, we start with a pitch like C, and we go whole step, whole, half, whole, 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 half. And that collection of 7 pitches, or a septichord, is called a major diatonic scale. And you can see it has this axis of symmetry. So if you rotate and reflect it, you get 12 diatonic scales. And what we can do if we sing in this scale, so most Western music is written in this scale, we usually assign solfege syllables to it. If you've ever sung in a choir, the first thing you ever learned was solfege. Do, re, mi, fa, sol, la, ti, do, right? Sound of music. Okay? And however, if we do that and we focus on Do or C, we get what's called C major. For instance, if we start and end with a C chord, then we say it's in C major. But if we take the same set of notes, but start and end on A or La, we get what's called the relative minor. So actually A minor, A natural minor, and C major are the same notes. The only difference is which note you emphasize when you play it. Okay? Now, what I want to do is I want to take this natural minor scale, I want to play with it. Instead of La, Ti, Do, Re, Mi, Fa, Sol, La, I'm going to take Fa and raise it a half step to Fi, and So and raise it a half step to Si. And this is what you do in a choir if you sing an ascending passage. Okay? And so it has a different name. It's called the ascending melodic minor scale. So La, Ti, Do, Re, Mi, Fi, Si, La. Let's listen to it, because we're going to build on this. So I'm going to play it twice. One more time. Okay. Now what I want to do, I want to take these 7 notes and I want to turn it into an octachord rather than a septichord. So what I'm going to do is I'm going to take Mi, I'm going to throw it away, and I'm going to replace it by Re and Fa. So we're going to get instead what's called the octatonic scale. Right? La, Ti, Do, Re, Re, Fa, Fi, Si, La. And you can see it's a very symmetrical object constructed from alternating whole and half steps. Let's listen to it, because Cohn's theorem that I want to focus on in my talk talks about this octatonic scale. Okay. Now, this is not as popular as the diatonic scale, but it is used. And we're going to listen to a couple of musical examples from it. The first example is from a 1974 rock album by King Crimson called Red. Okay? And in it, guitarist Robert Fripp, since he's going to be playing in this foreign scale, he plays 3 ascending passages of the scale so that your ears can get used to it. So what you're going to hear him playing is La, Ti, Do, Re, Re, Fa, Fi, Si, La, Ti, Do, Re, Re. He's going to play 3 times, then he's going to stop playing the song. So here's what an octatonic scale sounds like when you play it with music. then he drops down an octave and starts over. So this is the actual song. Okay, my second musical example is from a soundtrack. In 1959, Robert Heinlein wrote a very famous science fiction novel called Starship Troopers, and it was turned into a movie in 1997. And the soundtrack was done by Basil Polidorus. And in this novel, Earth is battling this planet of bug-eyed monsters. And anytime the bugs show up, Polidorus starts playing the octatonic scale. So you don't even have to see the bugs. You know they're coming because you can hear them. And we're going to hear it in the brass passages. Okay? We're going to hear it in the brass. So I'll point it out as we play it. So here's Starship Troopers. When the brass comes in. And then back down an octave. Anytime in the movie you hear this, you start ducking because you know the bugs are coming. Okay, so this octatonic scale is used, and we're going to explore next a mathematical property that it has. First of all, I'll point out that you can take that octatonic scale and break it into these two squares, right? There's a dotted square and a dashed square there. Those squares are called diminished seventh chords in music theory. So an octatonic scale is really two distinct diminished seventh chords played together. Okay? And for this reason, when it's used in jazz music, and it's used very commonly in jazz, it's called a diminished scale rather than the octatonic scale. And I also point out that if you rotate it and reflect it, you get three possible octatonic scales. One's shown solid, one's shown dashed, and one's shown dotted. We're going to take the solid one as a prototype just so we have a basic discussion. Okay? But what I say applies to all three. And so this will be our prototype octatonic scale, and I'd like to introduce the following notation for the time being. In a moment, I'm going to start writing down octatonic scales, but I won't bother drawing the sides of the polygon. And that means you need to know which notes are in the chord and which notes are not in the chord. The ones that are circled are in the octatonic scale. The ones that aren't are not. So please keep that in mind. And let me also remind you that we reduced all the possible intervals down to 6, right, because of our assumption of octave equivalence. If two notes are separated by one semitone, minor second, two semitones, major second, minor third, major third, perfect fourth, or tritone, and notice that the tritone geometrically is a diameter of the circle. Right. Now we need a definition, right? You knew we couldn't have a math lecture without a definition. Right? Well, here's our definition. Dyadic partitioning A collection of notes is said to be dyadically partitioned by one of those 6 dyad classes if it can be written as the disjoint union of dyads of the same class. So that's a mouthful. So let's look at an example. Okay. Here's our octatonic scale, the circled notes. And what I've done is I've connected them with 4 minor seconds. Notice that the individual minor seconds share no notes, and every note in the scale belongs to one of them. So we have partitioned or broken up the octatonic scale into disjoint minor seconds. It's dyadically partitioned by minor seconds. But you can do the same thing with major seconds or minor thirds. In fact, minor thirds you can do it 4 different ways. Or major thirds, or perfect fourths, or tritones or diameters. Okay? So notice we were able to take the octatonic scale and break it up into each of the 6 possible dyad classes. Okay? Cohn's theorem says that the octatonic scale is the only possible scale that you can do that with. So it has a certain special mathematical property to it, in inner symmetry or harmony, if you will. Okay? No other collection of pitches, including the diatonic scale, has this property. Now, Cohn discovered this theorem in 1991 when he was at University of Chicago. He's now at the Yale School of Music. But we have to get into a little issue of mathematical aesthetics here. The way that Cohn proved the theorem, once he discovered it, he proved it by going to a table of all possible chords. There are actually only 223 possible chords in this model. And he looked at all 223 and showed that 222 of them, it was impossible to partition with at least one of the 6 intervals. So this is what we call in math a brute force proof. Okay? And G.H. Hardy, great mathematician from the early 20th century, said it best when he said, "There is no permanent place in the world for ugly mathematics." See, we may have to live with an ugly proof for a while, but people will keep hunting until we find one that everybody can agree is beautiful. Okay? And Paul Erdős, the great Hungarian mathematician, I think said it even better than him, because he used to talk about the book. And when Paul Erdős talked about the book, this was a book that sits on God's desk. Okay? And in this book is the most beautiful proof of every mathematical theorem. Because, for example, the Pythagorean theorem, it has over 600 proofs, 600 known proofs to it. Okay? But in the book, one of them would be selected. Okay? And so when Erdős would see a particularly beautiful proof, he'd go, that one's from the book. That one's from the book. Okay? So I'm going to try to replace Cohn's ugly proof with something I hope at least has a chance of making it into the book. Okay? But first let me give you an aerial view of the proof before we dive into the details. Okay? First of all, if you're going to dyadically partition anything, dyads are 2 things. Well, the thing you're breaking up has to have an even number of elements. Okay? So that means we don't have to worry about n equal to 1, 3, 5, 7, 9, 11. Just have to worry about even numbers. And I'm going to argue that for n, by the way, is the number of notes in the chord or the scale. If n is 2, 4, 6, I claim you just don't have enough dyads to dyadically partition. Okay? For n equal to 10, we're going to show geometrically that there's no way to partition it with minor seconds. For a dodecachord with 12 notes, we'll give a geometrical proof that you can't partition it with minor thirds. And that will immediately winnow us down to n equal 8 octachords. And initially, it would seem like there's 3 possibilities. But when we delve into it geometrically, we're going to find that 2 of them will be excluded and will leave us with the octatonic scale as the last man standing. So let's take hexachords. Hexachord means you got 6 notes. If you're going to break that into dyads, then you're going to have 3 dyads, right? 3 times 2 is 6. But if you want to do that 6 possible ways, then you've got to have at least 18 dyads in the chord. But if you take 6 objects and select 2 without regard to order, you only get 15 possibilities. 15 is smaller than 18. There just ain't enough dyads in the chord to break it up in 6 possible ways. And clearly, if n equals 6 ain't going to work, n equal 4 and n equal 2 ain't going to work. So now, all we got to worry about is 8, 10, and 12, and we'll come back to 8. Right? For n equal to 10, well, think about taking a decachord and breaking it into 5 diameters, right? If you're going to use 5 times 2 is 10. There are only 6 possible diameters. That means the 2 notes that are not in the chord must be at the endpoints of the 6th missing diameter. And that says that if you're going to break it into diameters, then the chord has to look like this. It might be rotated, but this has to be the shape of the chord. And we have a basic problem here. If we go to 1 o'clock, here are the 2 minor seconds containing 1 o'clock. Okay? This minor second contains an excluded pitch. So we're going to have to include this guy in our partition. By symmetry, we're going to have to include that guy. But that leaves us in a dickens of a situation at 3 o'clock. Because these are the only 2 minor seconds containing 3 o'clock. We cannot include either of those because they're not disjoint from these 2. And that says we've painted ourselves into a corner. There is no way, okay, there is no way to break that up into minor seconds. So decachords are out. Moving on to dodecachords, okay, that's where you play all 12 notes at once. It doesn't sound very good when you do that. Okay? The problematic interval now is the major third, not the minor second. Because if we take this major third, and if we include that in our partition, then we have to exclude these 2 major thirds because they're not disjoint from them. But these are the only 2 major thirds that contain 12 o'clock. That means we cannot break this up into major thirds. And so 12 is out. And the only n left is n equal to 8. So let's think about breaking an octachord. It's got 8 pitches. You're going to have to break it into 4 pairs, right? Suppose we want to do that with diameters, right? Tritones. Then that means we're going to have to use 4 of the 6 possible diameters. That means the 4 pitches that you don't include in the chord have to be at the endpoints of the 2 missing diameters. And that says, for example, this, the octachord composed of these 8 uncircled notes, they cannot be diatically partitioned by diameters, right? Because the chords, the notes that are not in the chord are not at the endpoints of 2 diameters. And if you simply write down the possibilities, there are only 3 of them, right? See, here we have 2 diameters with no intervening pitch. Here we have 2 diameters with 1 intervening pitch. Here we have 2 diameters with 2 intervening pitches. Those are the only 3 possibilities. Okay? Now let's examine this guy on the left. We got a problem at 3 o'clock with minor thirds. Here are the 2 minor thirds, including 3 o'clock, but they also include these 2 pitches that are not in the chord. So that means we can exclude it. The problem with the middle picture is not at 3 o'clock, it's at 1 o'clock. And the interval is not minor thirds, it's minor seconds. Because here's the 2 minor seconds containing 1 o'clock. They both include an excluded pitch. So you can't include them in the partition. There's no way to partition that with minor seconds. And we finally have winnowed it down to this guy, and you notice what he is. Whole step, half step, whole step, half step, whole step, half step, whole step, half step. He's the octatonic scale. And that's the proof. That's the proof. And I claim that beats the pants off of writing down 222 different chords and checking out all possible ways to break them up. Okay. So that brings us back to the octatonic scale. It has been used by classical composers, Bartók, Debussy, Rimsky-Korsakov, Stravinsky. They all wrote many pieces in the octatonic scale. But I'm not going to play any of theirs. For my last piece of music, I gave in to vanity and I instead chose a piece that I wrote. Okay? So I'm going to play an excerpt from a piece called White Dwarf. And it's written in the octatonic scale, and I use all the mathematical machinery I could think of in this piece. I use all of the dyadic partitions. I use the factor groups, cosets, okay? Any mathematical angle I could think of, I included in this piece. But the music itself is what's known as program music. In program music, we try to portray sounds or objects musically. For example, Beethoven's Fifth Symphony. Dun, 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 dun. It's fake knocking on the door. Right? It's fake knocking on the door. So this is an attempt to portray the birth and death of a star, okay, musically. So I give you White Dwarf. So in 2007, I published this proof in the International Mathematical Forum, and actually I sent a copy to Rick Cohen, and he graciously said, acknowledged my proof was prettier than his proof. And it's become the standard proof in the area. For example, there's a recently published book called The Geometry of Musical Rhythm by Godfrey Toussaint, and he discusses Cohen's theorem in there, and my proof is the proof that's cited. So this is the standard proof of this theorem now. So my work has had some impact. Okay, that's all the music I had to present today. I just point out that this talk today brings to a conclusion my 40-year teaching career. And I mentioned that I have musical genes, but I also have teaching in my blood. My mother was a school teacher, and when my parents had a baseball team, right? They had 9 children, and my mother obviously had to give up teaching, but her house was a one-room schoolhouse. So we would be gathered around the kitchen table while she cooked, and one child would be learning how to read time, and the other one would be learning how to write. The other one would be learning how to write their numerals. Another one would be reading Children's Digest. So it was a little schoolhouse. So I was exposed to best teaching practices long before that term ever became current. Right? And I've spent my career trying to live up to that. And I was doubly blessed because I got to spend the last 22 years here at Kettering. And I want to thank you. Thank you.